So, as explained before, moist air is a mixture of dry air and of water vapor. Both of these two components, dry air and water vapor, can be considered as behaving as ideal gases. For dry air, this is due to the fact that the gases from dry air are very far from saturation conditions, and for water, this is due to the fact that the partial pressure of water is very low compared to the critical pressure of water. As water is very far from the critical point, even though the water vapor is quite close to condensation conditions, it still behaves like an ideal gas. So the Dalton's law states that when we have a mixture of ideal gases, the mixture itself behaves like an ideal gas, and the pressure exerted by each of the gases can be divided using partial pressure, and the ratio of the partial pressure from each of the components is directly proportional to the molar fraction of each of the components. The partial pressure of dry air is equal to the molar fraction of dry air times the total pressure, and this is the same for the partial pressure of water. So the partial pressure of both components will of course be lower than the total pressure that we have, and the total pressure in many cases it's atmospheric pressure. So this one is around 1 bar in almost all cases. So it means that the partial pressure of dry air and of water are both below 1 bar. But also the temperature is usually around ambient, so I would say something between 0 and 40 degrees Celsius. So in that case, there's also another condition for the partial pressure of water. This partial pressure needs to be below the saturation pressure of water that corresponds to the temperature of the air. And this saturation pressure is a direct function of temperature. This can be explained using the phase diagram of water. So the phase diagram is a very well-known diagram where the pressure is plotted as a function of temperature. So one thing you need to note from the beginning is that it's usually log-log scale. It somehow distorts a bit the shape of the different lines on this diagram. On this diagram, you can see, depending on the pressure and the temperature, what phase water is, and this can be either solid, liquid, or gas. And in the range of temperature at which we are, so between 0 and 40 degrees, this area is of interest. So this saturation condition between liquid and gas, so far from the critical point and from the triple point. So as I told you, this is a log-log scale, so we don't really see the exponential behavior of this curve if you plot it on a normal scale. I just did a zoom of this area on the next graph, and we can see that the saturation pressure is increasing exponentially with the temperature. So there's one point that everybody knows on this curve is that at atmospheric pressure, so at 1 bar, water is boiling at 100 degrees Celsius. But if we are, for example, at 20 degrees, like here in this room, the saturation pressure this time is only 0.023 bar. That means that the partial pressure of water needs to be below this pressure. If the total pressure is still 1 bar, it means that all the remaining partial pressure will be the partial pressure of dry air. So in most cases, the partial pressure of water will be very low compared to the partial pressure of dry air. This means also that the molar fraction of water is very low compared to the molar fraction of dry air. So moist air is mainly composed of dry air and of a little bit of water vapor. When the partial pressure of water equals the saturation pressure of water at the temperature at which we are, we say that the air is saturated. So this is called saturated moist air.